In this video, we will be covering F equals to LE, all right, where most of the time you're required to prove your Avogadro constant, which is L, okay? Now, so in your question paper, all right, at the last few pages, normally your question paper will provide you with a table that contains the important values, constant, and standards. So you can see they gave you a few rows of information in every chemistry paper, all right, as well as the periodic table. Now, and then what I want you to have a look is you want to put your focus on the Faraday constant, which is 96500 coulomb per mole. All right, that is how much quantity of charge is carried by 1 mole of electrons. Your Avogadro constant, all right, which is L. Okay, so this is 6.02 times 10 to the power 23. My advice is to always refer to your questions papers version of L. Okay, if you use like a older data booklet, you know, you will get to see things like 6.022 times 10 to the power 23. All right, so please always refer. I know that a lot of us have already engraved the Avogadro constant in our mind, but please go and use the number that is quoted in the question paper. All right, and the next number that we're going to look at is the electronic charge here, which is alphabet E. This is a charge carried by 1 electron. Okay, so therefore, these 3 numbers are provided, okay, and the formula is F equals to LE. Now, how did we even got the Avogadro constant where we conveniently use nowadays? All right, how did the scientists even come up with the 6.02 times 10 to the power 23? All right, so if you rewrite the formula, L equals to F divided by E. All right, what they do was they went and find out the quantity of charge in the electrolytic experiment, which is your F experiment wise, and they divided it with the charge on 1 electron. So therefore, that is how they get the Avogadro constant. So if you look at the units, Faraday constant is coulomb per mole divided by electronic charge, which is coulomb. So this coulomb and the bottom coulomb can be cancelled off. So therefore, Avogadro constant left with the mole -1 unit. All right. I want to elaborate a little bit more on the Avogadro constant first. The Avogadro constant or Avogadro number, there are 2 ways to define it. L, okay, equals to F over E, which is also mean the lengthy version, charge on 1 mole of electron, which is your Faraday constant, divided by the charge on 1 electron, which is E. Okay, so this one is the full length definition on the Avogadro constant. So this is one way to define L, Avogadro constant. Okay, now there's another way to define Avogadro constant, all right, which is the number of electrons divided by 1 mole of electrons. Okay, so that's why the unit also come out as mole -1. Okay, yeah. So this is 2 ways which are frequently used in this particular chapter when it comes to the quantitative part. All right. Yes, you may go back to year 10 or maybe SPM level, you know, where Avogadro constant is the number of, you know, atom or molecules that has exactly, you know, the same number of with your carbon 12. All right, the very long version. That one is also true. All right, but we're gonna more or less use these 2 most of the time for the calculation. Now let's look at an easy example first, which is taken from summer 22. So an electrolytic cell is set up to determine a value for the Avogadro constant L. The electrolytic is dilute sulfuric acid, or the electrolyte is dilute sulfuric acid, and both electrodes are copper. They use reactive metal here. When a current of 0.6 ampere is passed through the acid for 30 minutes, the anode decreases in mass by 0.35. State the relationship between Faraday constant and Avogadro constant. This is easy. F equals to LE, 1 mark. Right? It's like 3 marks. Okay. Number 2, use the experimental information in B and the data previously, all right, to calculate a value for the Avogadro constant. Okay. So first, we want to calculate the number of moles. Okay. So anode is copper because they said both electrodes are copper, and anode decreases. Okay. So therefore, first we're going to calculate the number of moles of copper. 0.35 divided by 63.5. Number of moles is 5.51 times 10 to the power negative 3. All right. Second thing I want to calculate is the quantity of charge passed in your electrolytic experiment. Q equals to IT, which is 0.6 ampere times 30 minutes, convert it to seconds. So the quantity of charge here is 1080. All right. So what we can see here is that 1080 quantity of charge, right, gave a 5.51 times 10 to the power negative 3 change in mass. All right. So we are looking at copper. So for copper, all right, theoretically, you need 2 mole of electron to deposit 1 mole of copper. All right. So can we find out 1 mole of copper require how much quantity of charge? So we're going to take 1 divided by 5.51. So let me calculate. It's 1080. So I've calculated to 196,007. This is experimental value, all right, that will give us 1 mole of copper deposition. Okay, now, so this is the total quantity of charge, but this charge was carried by 2 electrons, all right? So you need to take this divided by 2, right? Then we can calculate what is the Faraday constant in experiment version. So when you divide by 2, it means that 1 electron is 98003. Okay, let me divide by 2.6. Okay, so basically the number here is 196,007. All right, that can give me 1 mole of copper in the relationship. Okay, but because it's 2 electrons, we need to count what is 1 electron, which is what is the experimental Faraday constant. All right, so you can see it's similar to 96500. All right, but we calculated to 98003, but it's around there for 1 electron. Okay, so now L equals to F divided by E. Okay, so you are supposed to prove the value for the Avogadro constant. So L equals to F, which is your experimental F. So this is the charge on 1 mole of electron, okay, which is 98003, divided by the charge on 1 electron is called 1.6 times 10 to the power negative 19. So if you take the calculator and you press the number, you should be able to get an answer 6.125 times 10 to the power 23 mole negative 1. Okay, so the unit is not very important here, but number. All right, so you can see the calculated value, it's close to 6.02, which is your data booklet version. All right, but because this is an experimental data, so you're not going to get so accurate 6.02. All right, so therefore that is how we calculate Avogadro constant. So the tricky part is where when you calculate your quantity of charge, all right, which is the charge on electrons, right, you need to know that that total quantity of charge is actually carried by how many electrons. So you need to know who's your element, okay? So that will be the first example, which is a more straightforward case. Now we shall proceed with another example. Okay, let's look at the winter 1942 question 1. An aqueous solution of copper 2 sulfate is electrolyzed using copper electrodes. So they use copper electrode again, which is a reactive metal. Normally for us, when we do electrolytic in our syllabus, we normally play with platinum or carbon. We want an inert one, but they want to use a copper share. So a current of 1.5 ampere is passed for 3 hours, and 5.09 gram of copper is deposited on the cathode. So they gave you the charge of one electron is negative 1.6 times 10 to the power negative 19. Relative atomic mass of copper is 63.9. Very convenient. Thank you. All right. Use this data to calculate an experimentally determined value for the Avogadro constant and give your answer to 3 significant figures. Right. So if you would like to try it on your own, you may pause the video and try, and then perhaps after that, when you're ready, you can resume the video. All right. But for me, I will just continue to solve this question. So first, we're going to write the equation. So first, I'm going to calculate what is the number of mole of copper. Okay, so the number of mole of copper is this is the number of moles of copper. And the quantity of charge passed is 3 hours. Convert to minute, convert to seconds. All right, so what we can see here is that a 0.0802 mole, all right, was deposited by 16200 quantity of charge. So most of the time, we're interested to know what is 1 mole, all right, because most of the time the question is to deposit 1 mole of copper, what is the quantity of charge needed? All right, so I take 1 divided by 0.0 times 164. Okay. 201,995. 201,995. Okay, so that's for 1 molar. Okay, same thing. This is the total quantity of charge carried by your electrons. The question now is how many electrons is involved? 2. Okay, so this is your 201,995 quantity of charge. All right, that will give you 1 mole of copper. So the question is, what is 1 mole of electron? So you need to divide by 2. So 1 mole of electron is 100,997. So it's per electron. All right. Then you can conveniently take L equals to F divided by E, where your Faraday, experimental Faraday, is this number, divided by 1.6 times 10 to the power negative 19 given in the question. So the Avogadro constant will be 6.31 times 10 to the power 23 in 3 significant figures, 3 SF. Okay? Okay, I'm going to show you another way. All right, remember at the starting of the video, we actually have 2 ways of defining Avogadro constant, particularly for the calculation part here. Okay, the first one in red color pen, we have covered so far for the first 2 example, where we use the charge on 1 mole of electron, which is F, divided by charge on 1 electron, so-called your electronic charge, which is your E. All right, so we have been using this method. I'm going to show you the other way, which is to use the number of electrons divided by the mole of electrons. This is also another way to calculate your Avogadro constant. Now, the first one that we need to solve is what is the number of electrons, which is the numerator on top. Now, the number of electrons is actually your quantity of charge divided by electronic charge. This is the number of electrons. Total charge divided by electronic charge carried by electron. Therefore, you get your number of electrons. So the number of electrons involved in the experiment is 1.0125 times 10 to the power of 23. That is the number of electrons. All right. You're taking your quantity of charge divided by the electronic charge. Now, next, L equals to number of electrons, which is 1.0125 times 10 to the power of 23 divided by the mole of electrons. So the mole of electrons, okay, how do I get the number of moles of electrons? In the experiment, copper is 0.0802. Based on the stoichiometric equation, your number of electrons in the experiment is 2 times of 0.0802, which is 0.1604. So the number of moles of electron here is 0.1604. There, you can calculate your number. Calculated Avogadro constant is 6.31 to 3 significant figures to the 10 of power 23. Yeah, so both come up with the same answer. Okay, so actually you can choose one method. All right, you can choose one method to work it out. Okay, but it will be good that if you know both ways, all right, to calculate the experiment Avogadro constant. So I will highly recommend you to memorize what are the definition of Avogadro constant, which is F divided by E and number of electrons divided by mole of electrons. Okay? Now, so we're going to proceed to another example here. Now, this type of question, all right, they are quite guided, all right, but in a way, it can sort of force you to answer a specific number, all right? So you don't have the freedom to, calculate however you want, so long you get the final answer. So it can be a good thing, it can be a bad thing, all right? So let's look at this Winter 21. When dilute sulfuric acid is electrolyzed, water is split into hydrogen and oxygen. A current of X ampere is passed through the solution for 40 minutes. 462 centimeter cube of hydrogen are produced at the cathode because cation move to the cathode. And they are measured under room condition. Calculate the number of hydrogen molecules, all right, produced during the electrolysis, all right. Number of hydrogen molecules. When you hear number of atom, number of electrons, number of molecules, number of ions, when you hear these kind of few words, all right, they fall under the general heading called number of particles. So if you read a question that asks you to calculate number of particles, which includes atom, molecule, ions, electron, means you need to multiply with Avogadro constant. All right. Now, first, our hydrogen, we need to calculate the moles of hydrogen first. So the moles of hydrogen is 462 convert to dm cube and convert divided by 24, and the number of moles here is this. And therefore, you want the number of hydrogen molecule, you need to multiply the moles with Avogadro constant. So I get a 1.159 times 10 to the power of 22 number of hydrogen molecules. All right. Now B, calculate the total number of electron transferred to produce this number of hydrogen molecule. Number of electrons, number of hydrogen, right? They are number related. Okay, so first, you may want to take out this equation. All right. So this number here is the number of hydrogen molecules, And they want the number of electrons, which is here. So therefore, you just need to multiply by 2, all right? So you take this, you multiply by 2, hence the answer would be 2.3177 times 10 to the power of 22. All right. Normally we use mole and mole in the stoichiometry. So this time they use number of molecule, number of electrons. Okay. Now then, calculate the quantity of charge. Okay. So now remember just now the green color one, the second way we do about it. All right. Where Avogadro constant, okay, equals to number of electrons divided by moles of electrons. So they want the number of electrons. So what is the formula of number of electrons? Number of electrons is the quantity of charge, which is Q, over your electronic charge. So what is Q then? Q equals to I. Your I, which is, oh no, you're supposed to calculate the quantity of charge. All right, sorry. You're supposed to calculate the quantity of charge, which is Q. Okay. So now we have the total number of electrons. So therefore, number of electrons here would be 2.3177 times 10 to the power 22 equals to Q divided by 1.6 times 10 to the power negative 19. So hence Q will be 3708.32. Okay, so this formula is very important. So when they break it down, right, you are forced to answer. So because you don't have the freedom, all right, to prove until the Avogadro constant. Okay. Now the last part. Calculate the current. So the current pass here, since you got your Q, right? Q equals to IT. So Q is 3708.32 equals to X. Okay, so called I times your time. And your time is 14 minutes. Convert to seconds. So this is your time. So your ampere here will calculate out to 4.41. Okay, so what we learn over here, two things. You can use number of mole, number of electrons in the stoichiometry relationship because normally we use moles, and that is part B. Part C is where you realize the formula of the number of electrons is quite important. Number of electrons is defined as the quantity of charge Q divided by E, the electronic charge. All right? Right, so we move to the fourth example. Okay, so let's look at Winter 2142, question 3. Yeah? Pure water is a very poor conductor of electricity. However, when hydrogen chloride is dissolved in water, ions are formed and a current flows during electrolysis. The overall change after electrolysis is that hydrogen chloride gas is converted into hydrogen and chlorine. When a current of 3.1 ampere is passed through the solution for Y minutes, 351 centimeter cube of chlorine are produced at the anode. So anion move to the anode, chloride move to the anode to form chlorine gas, and it's measured under room condition. Calculate the number of chlorine molecules produced during the electrolysis. So when you see number of molecules, you should know that they want Avogadro constant to be used. All right, so first we will calculate the number of moles of chlorine gas. So NCl2 is 351 divided by 1000. So the number of moles is 0.0146. Then that will be the moles of chlorine molecule. So if you want number of chlorine molecules, you need to multiply with Avogadro constant. You're going to get 8.789 times 10 to the power of 21. Okay. Now next, calculate the number of electrons. So you need to bring your equation out. So I'm going to zoom in a little bit more, okay? Calculate the number of electrons. So, okay, so this is just the half equation. It does not really matter whether chlorine to chloride or chloride to chlorine. Okay, it's just we take the half equation from the data booklet, all right? Or if you want to, you can flip the equation to show 2 chloride donated 2 electrons to form chlorine gas, all right? If you really want to write in electrolysis form, but I just randomly take the equation out from the standard electropotential, which is in a reduction format. It does not really matter, okay? Now, based on this equation, all right, this is called the number of chlorine molecules, which is a number after multiplying with the Avogadro constant. That means on the left is called number of electrons, correct? That means on the right is called number of ions. That means they are related in stoichiometry, all right, in terms of particles, all right? Instead of mole, they use particles to relate, all right? Okay, so now, since we already know the number of chlorine molecule is 8.789 times 10 to the power 21, if you want to find the number of electrons, you just need to times 2, all right? So it's 2 times 8.789 times 10 to the power 21. So if you have to calculate this, you're going to get 1.76 times 10 to the power 22. Okay, calculate the quantity of charge. Okay, so remember the formula. Number of electrons equals to F, which is the quantity of charge. All right, or maybe I should use Q. Q, okay, divided by electronic charge. Okay, so number of electron equals to 1.67 times 10 to the power 22. So the quantity of charge is 1.76 times 10 to the power 22 multiplied by the electronic charge, 281, 2813, 2813, around there, 2813. 2816. Okay, if I use the full number, 2816. Okay, lastly, then this will be quite easy really at the bottom. Calculate the time in minutes. So you have Q equals to IT. So your I is 3.1 if you refer to the top part of the question. So hence your time, okay, so it's 2816 divided by 3.1. Time would be 908 seconds. If you want minute, you need to divide by 60. 151.4 minutes. Okay, similar, different variant, but same, winter 21. Okay, I think it's very useful. All right, now, the last question that I will be going through, all right, is taken from summer 15, okay, 41 question 5. Now, this particular question, especially for part 2, I think it may come easy for some, it may be difficult for some. Okay, reason is because, like I said, as you can see, the question is breakdown into bullet points. It's very specific. So that means the marks are awarded based on you answering the individual bullet points. So if you can't answer the bullet point, even though you managed to calculate the final Avogadro value, all right, I'm not so sure whether would you be able to get full credit. Okay, yeah. Even though the final answer for L, it will be the same. All right. So anyhow, let's look at this particular question, which is why I put it the last. Okay. First question, E1, state the relationship between Faraday and Avogadro constant. Straightforward. F equals to LE. Very straightforward. Now let's look at part 2. When the current of 1.2 ampere was passed through dilute sulfuric acid for 30 minutes, it was found that 130 centimeter cube of oxygen gas measured at 25 degrees Celsius and 1 atm was collected at the anode. So the anion moved to the anode and is hydroxide because it's dilute. And normally sulfate is not being discharged. So the following reaction takes place. They gave us the equation. Use this data and data from the data booklet to calculate a value for the Avogadro constant by calculating the 5 bullet points. All right. Now, so let's solve one by one. So the first one, number of moles of oxygen produced. So, okay. So number of moles of oxygen, let's take this 130. Okay. So this one is centimeter cube divided by 1000. So the number of moles of oxygen is 5.417 times 10 to the power of -3. So that's the moles of oxygen. So I'm going to write here 5.417 times 10 to the power -3 under the oxygen. Okay, see, this number is for the moles of oxygen. Now next, the number of moles of electron needed for this. All right, now if you already obtained the moles of oxygen, based on the equation, the number of moles of electron you multiply by 4 according to the equation. So after I times 4, the number of electrons here is 0.02167. Okay, so I'm going to put on the arrow here as well. 0.02167. This number of moles. Okay. Number 3, number of Coulomb pass. Okay, this is quite straightforward. Q equals to I times 30 minutes convert to seconds is 2160. Okay, so we have already covered the 3 bullet points. Now, number 4, number of electron pass. Okay, so you remember how to calculate number of electron pass? Okay, the formula. So number of electrons is defined as quantity of charge divided by electronic charge, which is 1.6 times 10 to the power of -19. Okay, so hence it will be 2160 divided by 1.6 times 10 to the power of -19. (1.32) 1.35 times 10 to the power of 22. Okay, so number 4 done. Last one. Okay, number of electrons in 1 mole of electrons. Now, I just want you to imagine, what if the examiner did not give you the bracket L? Do you understand what is number of electron in 1 mole of electrons? Okay, so I hope you know what it means. All right. Now, if you do not know what it means, it's okay because the examiner already put a bracket L. Okay, yeah. Now, you see, even if examiner gave L, Okay. A lot of students will start to think of F divided by E, okay, which is your experimental Faraday constant. And then after that, students don't know where to get the F. E, they know is 1.9, at 1.6 times 10 to the power 19. But the problem is they do not know what is F. Okay, now that's the reason why you have the other version called Avogadro constant is defined as the number of electrons divided by mole of electrons, isn't it? Okay, so if you look at what they write in the fifth bullet point, number of electrons in 1 mole of electrons. Okay, so there's two ways to calculate Avogadro constant. Now, if you're very fixated with the first one, F divided by E, then you're going to have problem calculating your F. Okay, yeah. So you need to use both formula. All right, you need to, know about these two formula because you do not know which one is needed to calculate your experimental Avogadro constant. All right. So please be prepared to know what is L. Okay, both version. So now you can take the number of electrons, which is the fourth bullet point, which is 1.35 times 10 to the power 22 divided by the moles of electrons. The moles of electron is bullet point number 2, 0.02167. Okay, so this would be the Avogadro constant, 0.02167. So what I've calculated over here in 3SF, 6.23 times 10 to the power of 23. Nice. Near to the theoretical Avogadro constant of 6.02. It's going to be around there. Okay, yeah. So I have already extracted 5 different questions, all right, underneath the heading called how do we prove the experimental Avogadro constant. All right, thank you for watching.